Hello everyone, welcome to another video of our multi-threading in Java series. If you haven't watched my last video, please go and watch it first because this is the continuation of last video. In this video, we will learn another important concept which is CPU's instruction reordering. We'll also see what are the issues with instruction reordering and finally what is Java's happens before guarantee. This is very important. Okay, so without wasting any time, let's start. In our last video, we saw how caching can cause race conditions, and to avoid that, we enforced our CPU to read and write from the main memory using synchronized keyword, right? So let's go into example and see that. Okay, so this was our example in which we were increasing the counter using two threads, and each thread will increment the counter to 100,000. So our final output should be 200,000. We saw how race condition occurred and our output was not actually 200,000. So we had to use this synchronized keyword. Okay, so we use this synchronized keyword to force the read and write of this counter variable from the main memory. Okay, at last I gave you an exercise where you had to use the volatile keyword and check if the race condition is actually avoided or not. Okay, so let's go ahead and do that. So let's get rid of this synchronized block and finally use volatile here. Okay, so if we use volatile here, all the reads and writes will be performed from the main memory, and if that is the case, counter's latest value should be visible to both the threads, thread 1 and thread 2, who are incrementing the counter, and so our final output should be 200,000. Okay, let's go ahead and run this main program. See, so what was the property of volatile? Property of volatile was it reads and writes from the main memory. But still, when we are running this particular program, instead of getting 200,000 as output, we are getting a number which is less than 200,000. Now let's go ahead and see why this is happening. Okay, so basically what we are doing is we have a counter and we are doing counter plus plus. Now this might seem like a single operation to you, but it is actually a multi-step process. So our first step is read the value of counter. Second step is to increment it. And our third step is to save the value of counter, right? Now what we have done is, instead of a plain counter, we have used volatile here, right? Since we have used volatile here, all the reads will be done from the main memory. So this will translate to read the value of counter from main memory, right? Now the value will be incremented. And the third is save the value of counter. Now since it is volatile, after save the value means write the value of counter, right? So where this write will be done? This write will also be done in the main memory, right? So volatile is doing what it is supposed to do. What is volatile supposed to do? It is to read and write in the main memory. Okay, so it is reading the value of counter from the main memory. Suppose the value of counter is 1. Okay, so it has read the value of counter from the main memory. Now it has incremented it from 1, it has incremented it to 2, and after this increment is done, then it will go ahead and save the value of this particular counter in the main memory. Okay, so if this is our main memory, value is read, then value is incremented, and then finally the value is saved in the third step. But what happens? We cannot guarantee the atomicity of these three steps, right? We cannot guarantee that all these three steps are performed in one single operation. What happens if it reads the value of the counter from the main memory? If there are two threads, suppose, if thread 1 reads the value of counter from the main memory, which is 1, right? It has incremented it, and at the same time, thread 2 also tries to read the value of counter from the main memory, right? we have used volatile, so it will go ahead and read the value of counter from main memory, which will be equal to 1 again, right? And post that, in the third step, thread 1 will go and save the value of counter in the main memory, which is 2. So it was incremented earlier, but it was not saved in the main memory, hence it was not visible. So it is not like volatile is not doing what it is supposed to do. It is doing what it is supposed to do, but since this increment operation is not an atomic operation, that's the reason volatile doesn't work. Okay, so always make sure to use volatile only on variables which are atomic. Okay, so suppose if you have a boolean field, boolean flag equals to true, this is an atomic operation. Okay, so if you change the value of flag from true to false, it will immediately be reflected in the main memory. No intermediate steps are there in between. Like this increment, there is no intermediate step in between. Okay, so this will directly be reflected in main memory, and if another thread comes and tries to read the value of flag, it will get it correctly, which is equal to false. Okay, so we have a thumb rule to always use volatile on atomic operations, right? So that's the reason it was not working. Now as soon as I remove this volatile from here and put synchronized, then this 3-step process is now combined in this synchronized block and it has become atomic, right? So that's the reason it was working in synchronized and not in volatile. So if you don't want to use synchronized also and volatile is not working, so what else you can do? So Java provides a type of integer which is known as atomic integer, and that atomic integer is responsible for making this counter plus plus operation atomic. Okay, so as the name itself suggests, so let's go ahead and modify this integer to atomic integer and see if this works or not. So atomic integer counter equals to new atomic integer. Let's initialize it with 0. Let's create getter and setter. Okay, getter and setter is done. Now instead of counter plus plus, we have a method in atomic integer which is counter dot increment and get. Okay, so it will increment the value, save it in main memory and get whatever the value is from the main memory. Okay, so this is done in our main. Let's go ahead and print counter dot get counter. Okay, now since this is atomic integer, this should work because all the read and write are happening in main memory. And yes, now you can see the value is 200,000, which is correct. No matter how many times I run, the value is 200,000. Okay, so there are 3 ways in which you can enforce the CPU to write in the main memory. The first way is use synchronized. Second way is used volatile, but make sure you use volatile only on atomic operations. And third one is to use atomic integer itself. Now let's go ahead and look into another important concept, which is instructions reordering. Now what is instruction reordering? Modern CPUs are fast and smart. Okay, so to optimize performance, they reorder instructions as long as the final result looks the same to a single thread. This is very important. They reorder instructions as long as the final result looks the same to a single thread. Let's take an example. Suppose we have 2 instructions to execute, int a equals to 1 and int b equals to 1. Suppose a single thread T1 is executing this, int a equals to 1 and b equals to 1. After executing this, what is the output? Output is value of a will be 1 and value of b will be 1, right? If I reorder this instruction and try to perform b equals to 1 first, b equals to 1 and a equals to 1, what will be the final output? A1 and B1, right? So even if I reorder this particular instruction, these two are completely independent, right? So the final value of A and B remains same, right? This reordering can be done. Now let's take another example where initial value of B, C, D and E are 1, 1, 1, 1, and these are the two instructions which we have to execute using a single thread. Okay, so if this is executed in order, so what will be the value of A? A will be B plus C, which is 1 plus 1, which is equal to 2, and value of B will be D plus E, which is equal to 1 plus 1 equals to 2. So this is the final value of A and B. Now suppose we reorder this particular instruction. If we reorder this, our first instruction become B equals to D plus E, and then A is equal to B plus C. Okay. So after executing this, D is 1, E is 1, value of B is 2. And then post that A is equal to B plus C, right? Value of B has become 2, value of C is 1, so A's value is 3. So our final output is B is equal to 2 and A is equal to 3. Okay. So we can see if we do not reorder the instruction, our output will be this. But if we reorder, our output will be this. So for the same thread, if we reorder the instruction, the final value of the variables can be different. And our CPU is smart enough to understand this. If the value of variables changes when we reorder the instruction, that means we should not perform instruction reordering here. Okay, as long as the final result looks the same to a single thread. But here the final result is not same, so this instruction reordering should not be performed by the CPU. Okay, now let's get to our third example where we have multiple threads. Okay, suppose we have two threads T1 and T2. These are the common variables which are visible to both the threads. One is flag, which is equal to false, data 1 value is 0 and data 2 value is 0. Okay, thread 1 is supposed to execute these three instructions and thread 2 is supposed to execute this one. Now let's take first case. What if CPU reorders these instructions which are supposed to be executed by thread 1? Without any reordering, what will be the final value? Data 1 will be 42. Data 2 will be 45 and flag equals to 2, right? If reordering happens, will it affect anything? These three are completely independent. So even though reordering happens here, the final output will remain same. So reordering is possible here, right? Now what should be the ideal output of this particular program? So data 1 should be set to 42, data 2 should be 45, flag should be equal to true. As soon as flag becomes true, this particular condition will be executed for thread 2. Flag is true and it will print 42 and 45, right? This is the ideal output that we should have. Now if reordering happens, suppose data 1 is set to 42 and after this particular instruction is run. Flag is equal to true, right? And in the middle of that, thread 2 sees that the value of flag is true. Value of flag is true now and it will start and print data 1 and data 2. Now value of data 1 is 42. Value of data 2 is not yet set. So what will be the value of data 2 printed? It will be equal to 0. So this is not the output that we expect, but this can happen if CPU reorders the instruction, right? Now let's go to case 2 and see if CPU does not reorder. If CPU does not reorder, do you think this particular program is totally correct? So let's see. So if CPU does not order, data 1 will be equal to 42, data 2 45 and flag equals to true. But if you remember from our previous lecture, these three values are not guaranteed to be stored in the main memory, okay? So for thread 1, this particular change in value might be stored in the registers itself, right? And we also don't have any visibility that when will data 1 be flushed, when will data 2 will flushed, and when will flag will be flushed in the main memory, okay? We can also not guarantee which among these three will be flushed first into the main memory. So the order of execution of instruction is this, right? But it might be the case that flag equals true is flushed first in the main memory. From registers to main memory, value of flag is flushed, but data 1 and data 2 is still kept in register for some time. And in between that, thread 2 goes and start executing its instruction. At that particular time, the value of flag read from main memory is true, and it will print data 1 equals to 0 and data 2 equals to 0, because value of data 1 and data 2 are still in the registers. So even if CPU does not reorder this instruction, still there is a possibility that incorrect value of data 1 and data 2 is read by thread 2, because we cannot guarantee the order in which the value of all these variables will be flushed in the main memory. Got it? Now, how to resolve this? So we cannot control whether instructions are reordered or not, right? But we can do one thing. If you go ahead and initialize this particular flag as volatile, okay? So if we go ahead and make this flag as volatile, then what will happen? So this is basically volatile. Okay, as soon as you write volatile here, so the CPU knows that it can only reorder the instructions which are before this volatile variable among themselves, okay? So CPU can go and do data 2 equals to 45, data 1 equals to 42. It can reorder these two instructions, but it cannot reorder this particular instruction as soon as you write volatile. There is also one more thing to notice here. Suppose if there was data 3 equals to 46 and data 4 is equal to 47 after this, okay? So suppose these were the 5 instructions that thread 1 has to execute. These two, then volatile, then these two, okay? So as soon as you write volatile here, CPU also knows that mixing of instructions which are executed after this volatile variable is set to true is also not allowed, okay? So CPU cannot reorder and perform data 1, then data 3, then data 4, then data 2, then data 4. So this is mixing of instructions which are above and below the volatile variable, okay? So this is also not allowed. What is allowed is you can reorder the instructions which are before the volatile flag and reorder the instructions which are after the volatile flag among themselves, okay? So let's see what happens as soon as you write volatile here. As soon as you write volatile here, you have restricted the instruction reordering till here itself, right? Okay. So when data is equal to, data 2 is set to 45, data 1 is set to 42. As soon as you write flag equals to true, what is the property of volatile? You are setting the value of flag is equal to true. So as soon as this instruction is executed, value of all the variables which are visible to the thread are flushed to the main memory. So value of data 1, data 2 and flag itself will be flushed to the main memory. Okay, so main memory will have data 1 equals to 42, data 2 is equal to 45 and flag equals to true, right? Not just flag, all the variables which are visible to the thread, their values will be flushed in the main memory. So this is flushed in the main memory. Now when thread 2 goes ahead and executes this particular instruction, it sees the value of flag is true. What is the value of data 1 and data 2? Value of data 1 and data 2 is equal to 42 and 45. So it prints 42 and 45. To ensure that we have the ideal output that we want, we need to keep in mind instruction reordering in place, and you have to initialize the flag value to volatile here, okay? So this is what is known as happens before guarantee. Volatiles happens before guarantee, okay? So all the instructions which are before the volatile flag will be reordered among themselves and their execution is guaranteed to happen. it is guaranteed to happen before the volatile variable. Okay. And similarly, for all the instructions which are after the volatile flag will be reordered among themselves, right? And their execution is guaranteed to happen after the volatile flag. Okay. Never ever there will be a case where these two set of instructions which are present before the volatile and after the volatile, they won't be reordered among themselves ever. Okay. So this is what is known as volatiles happens before guarantee. And this same guarantee is given to us by synchronized block also. Okay. Suppose there is an instruction data 1 equals to 42, data 2 equals to 43, synchronized. This is a synchronized block and you are performing some XYZ operation, right? And data 3 equals to 45, data 4 is equal to 46. Okay, in this case also, synchronized also does the same thing. As soon as CPU sees this synchronized, CPU knows that it can only render the instructions which are before this synchronized block, and mixing of the instructions which are executed after this synchronized block is not permitted. Mixing of these instructions and reordering are not permitted. These can be reordered among themselves and these needs to be reordered among themselves. And this is also one of the guarantee that synchronized gives. So this is known as synchronized happens before guarantee. Okay. So all the instructions which are before the synchronized block will be reordered among themselves and their execution is guaranteed to happen before the synchronized block. It is known as synchronized happens before guarantee. Now let's take a real world example. It is actually the same example, but just to make things more clear, let's take an example and solve it. Okay. Suppose we have two threads, thread 1 and thread 2. Thread 2 is supposed to perform these two operations. Burger is ready equals to true, note on counter equals to true. If note on counter, then serve burger. Okay. What is this note on counter? This note on counter means, so chef prepares this particular burger. After the burger is ready, chef leaves the note on counter and this counter indicates that burger is ready. Okay. So thread 1 is chef and thread 2 is our waiter. As soon as waiter sees that note on counter is equal to true, it goes ahead and serves the burger. Okay. Now, suppose if we do not use volatile here, what will happen? Suppose instruction reordering happens. Instruction reordering happens and note on counter is executed first and set to true. And also, for some reason, CPU decides to flush it out to the main memory. So in main memory also, note on counter, note on counter variable's value is set to true. Thread 2 waiter is constantly seeking what is the value of note on counter. It sees the value of note on counter is true and it goes ahead and serves the burger. But the burger is not ready yet, right? It was CPU who performed instruction reordering, and before the burger is ready, it goes ahead and puts the note on the counter, which is incorrect. So to solve this, what we need to do? Pause for 5 seconds and think what you need to do here. To solve this, you just initialize this note on counter variable to volatile, right? As soon as this is volatile, no instruction reordering will happen. When the burger is ready, post that, note on counter will be executed. As soon as note on counter is executed, all these values are flushed in the main memory, right? And after that, waiter sees the value of note on counter is true and it goes ahead and serves the burger. And this time he finds the burger actually, right? It was not a false alarm. This we solved by using volatile variable. Okay, so this is a very important thing that you need to keep in mind wherever you receive these kinds of bugs in multi-threaded environment. You also need to take care of instruction reordering that happens within the CPU. I think we can stop this video here, but let's do a recap of what we have learned in Java memory model. Okay, so we have learned about registers, caches and main memory. We have learned what is race condition and how caches can cause race conditions, right? We have learned about instructions reordering. What are the issues that instruction reordering brings with it? What is volatile happens before guarantee and what is synchronized happens before guarantee, and how these two tackles in the problem that we get during instruction reordering. Okay, so go ahead and revise all these concepts. In the next video we will look into a brand new concept called semaphores, and most importantly we'll also solve an interesting problem using semaphores. Okay, so until the next video, stay safe, stay healthy, bye bye.